Moseley. So what is Moseley's law in periodic table? Tell me. Moseley's law in
The properties of elements are periodic functions of their atomic number.
correct. So the physical and chemical properties of element is periodic function of atomic number, not the atomic mass, which was the Mendeleev hypothesis, right? So from the X-ray, we modified the Rydberg formula and we said that the 1 by lambda is equals to R into Z minus screening constant whole square. So what is A? Screening constant, and on what factor? On what factor screening constant depends? Tell me guys, on what factor screening constant depends?
It depends on number of electrons and in which subshell they are.
Correct. So can we say it depends on the electronic configuration?
Yes.
So it depends on electronic configuration. And because it depends on electronic configuration, so can we say the electronic configuration is property of individual atom? Or you can say atomic number? Because atomic number will decide in a neutral atom how many electrons are there. And number of electrons will decide the electronic configuration, and the electronic configuration which in turn will decide the chemical properties, isn't it?
Yes, sir.
And electronic configuration also decides the various physical properties like boiling point, melting point, and so on, isn't it? Also, the property like the magnetism, like paramagnetic, ferromagnetic, diamagnetic. So all these are function of configuration of electron. Now configuration will take care of all the quantum numbers. So we have principal quantum number, we have the azimuthal, magnetic, spin. So we say that it depends, it decides the everything. Okay, just a moment, I will make a change here. Just, we call it B. That's it. So now what you can do is you can multiply both sides with C. So C by lambda is how much? RC into so mathematically, which graph is simple graph to plot? The linear equation, right?
Yes.
So we can take square root both sides. The square, the quadratic becomes non-linear, like this, isn't it? And C by lambda is called frequency. And now you can see there is a term here, RC 1 minus 1 by n square minus 1 by m square. This entire term we call actually A. And if you compare y equals to mx plus c, what is m here? M is
A,
and c is
AB,
minus AB.
sorry, minus AB.
Now the square root of frequency, this is the square root of frequency. And this is the atomic number. And the square root of frequency versus atomic number, if you plot the graph is going to be a straight line, right? So is it a perfect straight line? The answer is no. The experimental line is not a straight line. This is the rough approximation. So when actually he plotted the graph versus square root of frequency versus atomic number, and if you plot the elements, the graph, or you can say the elements will, populate this particular way. And then you can draw the best fit curve. The best fit curve will be like the one which passes to the center of mass. Something like this. And of course, this will be very close to the origin, but need not to be going through the origin because we have the negative intercept. If I extend this line, because the graph not be negative, so we have to extend this line. And once you extend this line, the intersection will be how much? As per the Moseley law? Minus AB, isn't it?
Yes,
So this is your minus AB, and if I call this as theta, so we can say tan theta is how much? The A, right? This is tan theta, the slope is A.
yes,
Yes.
So we can see there is a, a linear relationship between the square root of frequency and the Z. What Moseley did was he performed this X-ray and he obtained the characteristic X-ray, and particularly he obtained the K alpha radiation. And when he plotted the graph of the square root of frequency with Z, he got close to a straight line. And that was also evident from the Rydberg equation after modifying for the many electron system. So for many electron system, we need to modify the Rydberg equation, and the B will come into picture. And this linear property or a relationship was the proof that the K alpha frequency, the square root of K alpha frequency is proportional to Z. In a way, it is function of Z. And from there, he deduced that the physical and chemical property of any element is periodic function of atomic number Z. And that was the beginning of the modern chemistry or modern periodic table as we know it today. So for K alpha, okay, we'll talk about A again. What is A here? RC into. Now, what this represents? Can you guess? This represents nature of transition. Nature of transition. Now, if I ask you, the A depends on property of element, yes or no? Does it depend on property of element? Is there any dependency of A with element? Or is it going to be same for all element for a given transition? Will it depend, yes or no?
Yes, sir.
No,
But N
depend.
and M are just name of the orbit number, right? R is
For
fundamental constant, C is constant. So how does it depend on element? Tell me.
no, I do not.
So A is called transition constant and it is independent of element. This is called transition constant and remains independent of element. But B is screening constant. So it depends on element. For the obvious reason that every element will have unique configuration, or you can say unique distribution of electron. So they will kind of screen or shield the nuclear charge differently. And Z minus B is called, what we name it? Effective
atom.
nuclear charge, or you can say JE. So if I multiply with effective atomic number, that's better way of saying.
Effective atomic number.
Yeah. Effective nuclear, you can say, how to say it? Yeah, atomic number is the only way. Okay. But number is not right way. I mean, let's call this as into E. Just we can multiply with no, this is better of saying effective nuclear charge. So Z minus B into E is called the effective nuclear charge, and this is the effective charge that the electron will experience who is transiting. And because A depends on transition, so the moment to decide which transition you are talking about, the A will have the ready-made answer. So we can say for K alpha, we know the transition is from where to where. Alpha means you go to the K shell.
Yes.
Alpha means the transition is from any shell to the K shell, right? So these all are alpha, lambda K. So these all are lambda K. And because we're coming to alpha, so this is lambda K, and nearest will be K alpha, the next will be beta, the next will be gamma. Okay, we don't have space. So K alpha means what? Coming to K shell from the nearest point, nearest orbit. This is 2 to 1. So the value of A will be how much? RC into 1 minus 1 square minus 2 square under root. A turns out to how much? 3 RC by 4. This is the fixed value. What you are supposed to remember that for K alpha, default value of B is taken as 1. And therefore the Moseley equation for K alpha, if I write mu K alpha, then you can write as 3 RC by 4 Z minus 1. Only for K alpha. So for K beta, should we take something else? The answer is no. For K alpha, K beta, K gamma, they will give you some value, or from the given condition, you have to derive the value B also. Only the default value we can take is 1 for K alpha. For others, we are not supposed to take the default value. So in fact, there is no default value. We all have the experimental value. And we have to use that value to derive the answer. So that is your Moseley law, which is very simple. So what we'll do is we'll solve few questions to get the hang of it. So I hope you all have SEO.
Yes.
So we'll start with the solved example. Go to the solved example of X-ray. And you can see in the solved example, we have something question number 4. Can you read the question 4? It is clearly saying that find the constants A and B in Moseley's spelling is wrong. Huh? I was thinking that it is M-O-S-E. So find the constant A and B in the Moseley's equation from the following data. And wavelength is given for the K alpha. For molybdenum is given, and for cobalt is given. So we have two equations, two unknown. So you can solve it, isn't it?
Yes.
So question number 4, SCV worked out example. Don't see the answer. Just hide it and solve the answer. First question, element is given. Z is given. Wavelength of K alpha. So because lambda is given, you can use the lambda relation. So instead of a square root mu, you can use C by lambda. And then two equation, two unknown, you can solve it, right? So try to write the equation and solve the answer. Then we'll go to the unsolved example. Don't see the solution. Done, guys? Anyone able to solve the entire question?
1 minute, sir.
See, even these kind of calculation you can expect in the examination. So it is good to practice right away. Done, guys, come on. Is it done? Jess, you got the answer?
Just a second.
Dars, you got the answer?
So just doing the final calculation. 1 second. Yes, sir.
You can check the answer. Is it matching?
They're a bit off.
Almost.
But 50.7 and 1.43.
Okay.
The 5.07.
No, it's the plain calculation. You are supposed to get the answer. If it is not matching, just redo the calculation. But now we'll go to something next because we cannot linger on the same problem.
Probably because of the approximation.
Okay, so now come to the objective one. So in objective one, you have, don't see the answer. We have 14 questions. And the time I'm going to give you is 14 minutes only. So objective one, 14 minutes, all questions, everyone. Exactly 14 minutes, we'll stop it. Not 14, I'll give 12 minutes. Objective one. Do it. Because I think there is no calculation, just one or two calculations. And try to do it as fast as possible. Read very intensely, understand, solve it without losing focus. So for the next 12 minutes, 100% focus. Everyone start. $14 questions, 12 minutes. How fast you can read, how fast you can answer. So I hope you all have started.
Yes, sir.
Fast. 1 minute left. All done?
Yes.
So you all are ready with your answers?
1 minute.
Yeah, 1 minute is only left. So no one will see the answer. I will tell the answer, you will match the answer and see how many are correct, how many are incorrect. So I trust you guys that you are not seeing the answer. Okay, done. Stop. Now match the answer. 1D, 2A, 3D, 4C, 5C, 6A, 7D, 8C, 9A, 10B, 11D, 12D, 13D, 14B. Tell me how many you got correct, one by one. So how many got more than 12 correct? So simply raise your hand, those who got more than 12 correct. More than 12, one got correct. More than 10. More than 10. Correct. More than 8 correct. More than 8 correct. More than 5. Not more than 5. Less than 5. Less than 5 correct. Less than 5 correct. Less than 6 correct. Less than 7 correct. Okay. So those who got more than 12, more than 10, I mean not more than, I would say, not less than 6. Okay. So tell me if I need to discuss any question out of 16, out of 14 question. Which question you want to discuss? Tell me.
So could you go to the previous slide? I wanted to check.
12th question.
Okay. Which one? This one?
No, the next one. Yeah. Sir, 6th one.
Moseley's law for characteristic equation in this both A and B are independent of material. A is independent, but B dependent. So B is correct, na?
B should be correct, right?
Yeah, B should be correct.
A, right?
Because A is given.
Yes, sir. Yes.
Six answer given is A. A is given. This is incorrect. A is independent, B is dependent. Change this.
Okay.
Yeah, A is independent, B is depends. This is incorrect answer given.
12.
12. 50% of the X-ray coming from Coolidge tube is able to pass through 0.1 mm thick aluminum foil. The potential difference between the target and the filament is increased. The thickness of aluminum foil, which will allow 50% of the X-ray to pass through, will be. So, do I need 50%? Now it's more energy. So for 50%, what we need? A lesser thickness or more thickness?
More.
The thickness of aluminum foil, which will also, of course, we need more thickness, huh?
More thickness. Yes.
Because see, we have more energy. So to now see the penetration power depends on the kinetic energy, like how much energy you possess. So that will decide the penetration. Because penetration basically means you make multiple collision, and through every collision you cross some layer of metal, and you lose energy. So now, if you have more energy, so to reduce by 50%, we need more layers, isn't it?
Yes.
Understood what I'm saying?
Yes.
Yes, sir.
So that is logical only. Any other doubt?
The 10th one.
10th we have discussed, right?
Yeah.
So what they are saying, so which K alpha is having lesser wavelength?
The second one. More potent.
The dotted one, no?
Yeah.
The
Yes.
dotted having more lesser wavelength, so more energy,
Yes.
and more wavelength is less energy.
Yeah.
So the transition is the K alpha here is happening because more energy means it is bigger Z actually, more Z. So dot
Yes.
will have the dotted line will have more Z, isn't it?
Okay. Yeah.
Same transition, more energy.
Yes.
So Z must be more.
Yes.
Same transition, more energy. So Z must be more, no?
Ah.
Can you find the right answer? And also you can see the continuous ray is, so the peak of the continuous, the cutoff, you can see the cutoff of continuous. So which one is having lesser cutoff? The bold one.
The solid one.
So cutoff means the kinetic energy through the acceleration, through the accelerating potential. So lesser the cutoff, more the potential difference, isn't it?
Yeah.
So bold will have more potential difference than the dotted. Can you check?
Understood. Understood.
So we have to check two things. One, the cutoff one, where it begins, and the spike, we have to check the lambda. You will get the right answer. So how many of you got this answer correct? The 10th one. Everyone. Very good. So you all got correct.
Yes.
Any other doubt? No doubt. Now, again, don't see the answer. Objective 2, we have 8 questions. The time I'm giving you, 10 minutes. Start. From the JEE-Mains point of view, these questions are more important. Don't see the answer. Just solve it, read carefully, very carefully, and solve 8 questions. Read each and every option very carefully. Everyone. Very, very carefully. Spend time. If you're able to solve 5 questions in that 10 minutes, that's okay. 2 minutes left. Time up. So match the answer. 1 CD, 2 B, 3 B and C, 4 C and D, 5 C and D, 6 B and D, 7 all, 8 D. Okay. So how many of you got more than 3 correct? More than 3 correct. Okay, only. Okay. Okay. More than 3 correct. More than 3 correct. Okay. More than 5 correct. More than 5. More than 5. More than 6. Like 7 or 8. All correct. Okay. So let's discuss the doubt. Tell me like which question I need to discuss first. Tell me which question I need to discuss. One, any doubt in one?
Sir, can you one tell sixth one?
when an electron strikes the target in the Coolidge tube, its entire kinetic energy is converted into photon, maybe converted is contained to it. So is incorrect. So it may be converted. Okay. So maybe converted into photon, maybe converted into heat. Yeah. So B and D is possible answer. What is the answer given? 6.
B and beyond.
6 is B and D only. No? So may means you cannot say with 100% surety. That's why it's may. So we cannot be a certainty because every electron undergoes infinite collision, not single collision.
Yes. Okay.
Then another doubt. 7, 8, 1, 2, 3. Any doubt in this? 4, 5, 6, 7, 8.
5, 5th one.
5th one. What is your doubt?
Sir, I'm little doubt in the B, I think. B and C.
So the minimum wavelength will decrease, na?
Yeah.
More energy means less wavelength. So cutoff will decrease. As you increase the potential, the kinetic energy will increase. K equals to EV.
Yes.
So V will grow. So we know this is SC by lambda cutoff. So lambda threshold or cutoff is how much? As V will increase, lambda will decrease.
Oh, yes. Mistake, yes.
Sir,
Yeah.
sir, in the 8th question, it's given that both the photons are of the same wavelength. So that is the reason, like, option D should be the correct answer. Right?
Consider the photon of continuous X-ray and photon of characteristic X-ray of the same wavelength. Okay.
Yes.
So which of the following is are different for the two photons? Frequency, energy, method of creation, penetrating power. So what do you think?
Option D, right? Because frequency and energy will be same. Same wavelength.
Yeah, so they have same wavelength, so they must have same
Yes.
frequency, right?
Yes, is that only I'm asking.
So they must have same energy also.
Yes. Yes.
So they're asking what is different?
Yeah. Method of wave.
Only method of creation, no?
Yes.
So next is okay. If you want to, if you have the confidence that you can go to the next topic. If you want some more practice, then you can solve the first few questions of exercise just to get the hang of it. Because all are formula based. Like there's nothing like your particular brains. So if you want, you can start with question number 1 to question number 5, and then solve question number 17 to question number 21. That's it. Just for practice. So solve 1 to 5 and solve 17 to 21. 20 something. The easy one and the mostly this is the basic relation, energy relation. This is mostly. For this, how much time you need? Tell me. 20 minutes or 15 minutes? How much?
Sir, 15.
Okay, so 15 minutes is good enough. Solve it and then I'll go to the nucleus chapter today itself. I have to finish this nucleus. So 20 minutes, yeah. So from 11:30 I'll start, and hopefully in 1.5 hours we should be able to finish the nuclear physics.
Sir.
Yeah.
Sir, this nucleus chapter is the last topic for the entire chapter, modern physics.
Yeah, it is the last chapter. So it will have nuclear physics and radioactivity both.
Yes, sir.
Yeah. Then photoelectric effect I am not teaching because it is already taught in chemistry many times. But if you want, then that can also be covered.
Yes.
Or we can do only numericals from SC Verma. Or do you need some theory also? Tell me.
So numericals will be enough for me.
Yeah, so fine. We'll solve numericals. So solve 1 to 5 as fast as possible. And 70 to 20 again as fast as possible. And then I'll go to nucleus. So 11:30 I'll start the nuclear chapter. Till that time you can solve as much as you want. I will just mention the fact that yeah, A is transition constant, B is depends on element. For JEE, assume because this is a very approximate model. It's a good fit actually. So it is anyway not accurate. Okay, so now we'll move towards the second part of modern physics, which is called the nuclear physics. So we know that every nucleus will have what it will have? Protons and neutrons, right? So in case of nucleus, we know that it will have proton and neutron because we know because we have read in the class 9, 10th, 11th, 12th, whatever. Okay. Together they are called. So protons
Nucleons.
and neutrons reside inside nucleus and together we call, what do you call? Nucleons.
Nucleons.
Okay, but this is not the only region we call nucleons. The other region which we should be aware of, inside nucleus, P and N are indistinguishable. I don't know the spelling is correct or incorrect. Tell me the correct spelling. Indistinguishable. Very difficult. What should be the spelling of indistinguishable?
IIT.
One second.
DIN.
Indis.
INDIS TIN GUISH ABLE.
Oh, so I think, quite close.
Yeah, just one
Yeah.
H also.
So inside nucleus, P and proton and neutrons are indistinguishable. So we cannot say which one is proton, which one is neutron. Their identity is revealed only when they come out. Okay. So it is like they are twin brothers, and one is wearing the crown, other is not wearing the crown. So let's say because they are twin brothers, so once they will come out, so the one which you will see with crown, you will say it's a king. And if it is coming without the crown, we say It is a regular one, like a normal human being, not a king. The thing is, protons and neutrons are made of something called quarks.
Quarks.
So proton and neutrons are made of quarks. So I will present the quark model of nucleus. So there are two types of quark. There are many, but we'll consider only two types. So we have up quark and down quark. For up quark, we use the symbol U. And for down, it's a D. Very simple. An up quark having mass, let's say Mu, and the down quark, let's say mass is Md. What we need to know that the down quark is slightly heavier than up quark. So the fact which we should know that Md is more than Mu, but they are roughly equal, just on a greater side. So we all know that the proton itself is very, I mean, these are not very heavy particles. So the mass of neutron is slightly okay. We'll come to that. So down quarks are slightly heavier than up quark. Now, if we talk about the proton, so proton, okay, one more thing. Let me talk about the charge. So charge of up quark is how much? 2/3 of electron plus 2/3 of electronic charge. And the charge of down quark is
-1/3.
So down quarks are negative and up quarks are positive. You can think this way. Okay. A proton is made of UUD, which means 2 up quark and 1 down quark, whereas the neutron is made of UDD, which means 2 down quark and 1 up quark. And now you know the reason why neutron is assumed to be slightly heavier than proton.
Yes, sir.
So the mass of proton and mass of neutron are roughly equal, but still the neutron mass is on a higher side. And that is the reason why the rest mass energy of proton and the rest mass energy of neutron, if you want to write, the En will exceed the Ep. Okay, so these are very important idea which we need to use actually in the future. Now, because it's a UUD, you can also find the charge. What is 2U? 2/3 plus 2/3 minus 1/3 into E. So charge of proton is how much? If you add all this thing, what you get? E. Is neutron really neutral? The answer is the net charge is neutral, but neutron is not a neutral particle. It is having some charge. So the charge on neutron is 2/3 minus 1/3 minus 1/3. The net is 0, isn't it?
Yes, sir.
But it is having charge. I'm saying it is not like completely not made of charge. It is having charge. The reason is net is 0. Okay. So if you draw the diagram of neutron, so it will have a positive layer and negative layer. And the net charge is 0. Now, within nucleus, nucleon, as we say nucleon, these nucleons undergo charge transfer. So they keep on exchanging the charge. Which means there is a configurational change of quark level. So at quark level, because We can convert the up quark and down quark by simply change of energy. Because in the world of Einstein theory, energy is mass, mass is energy, both are equivalent. So a proton and a neutron, to just change from one form to other form, they exchange the quark, and so they keep on share the charge. So you can think that because every charge is carried by the quark, so as you exchange the quark, what will happen? They also change the energy. So there is a continuous change of quarks, and therefore at some instant the p will be the left will be p, right will be n, but at next moment the left will be n, the right will be p. They keep on exchanging from p to n, n to p, p to n, n to p, p to n, n to p, and this happens at a very rapid, you can say, rate. So the frequency of conversion is extremely high. It means it is impossible to distinguish which one is proton and which one is neutron. Now let's say you can think like they are twin brothers playing the frisbee, frisbee. How that frisbee? FIRS, FIRS.
Yes, sir.
This one. Are we right? I don't know. So let's say they're playing the frisbee. Okay, and they are playing this inside the nucleus. So the only difference between you and your sibling is who is holding the frisbee. Okay. It may be in air also, right? So when you click the photograph, the frisbee is neither with the left one, the right one, neither with you or your brother. It is in air. But let's say due to some nuclear reaction, they are thrown out of the world of nucleus. By some reaction, they are thrown out of the world of nucleus. Then there are only two possibilities. Either you will go outside with frisbee, or you will remain inside. Or so you will go outside without frisbee. So it is like whether you will go outside with charge or you will go without charge. When you go with charge, then you will be designated as proton. And when you lose your charge inside the nucleus and you just come out, you become neutron. So the identity of proton and neutron is only when they come out of the nucleus. Within the nucleus, they don't have any such identity. The reality is a nucleus is a jumbled world of quarks. So what is nucleus? A jumbled world of quarks. And also you cannot distinguish the UUD of first proton with the UUD of second proton with UUD of third and UUD of fourth. So all this UUDD, UDD, UUD, UDD, or DDU, whatever. So all are mixed up. So this is DDU, UUD, DDU, UUD, and so on. It is completely as a field. So what it is filled with? It is filled with a large number of quarks. Okay, depending on how many nucleons we have. And these quarks are converting from one form to other form. So the up is becoming down, down is becoming up because of some reaction is happening. So what we need to remember that we know in the atom that the atom will have stationary orbits in which electron will move. It will have definite quantum state, and a particular configuration will have one quantum state. As you change the configuration, its quantum state will change. And the quantum state is also the manifestation of energy carried by the atom. So similarly, a jumbled world of quarks with U, D, 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 U, U, D, D, U, and so on. It is also one configuration. Okay. And a different collection of U, D, 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 U. Or you could say different configuration means how many up quarks you have, how many down quarks you have, how they are rearranged, how they are located, are they together, are they separated? Okay. There, one particular configuration gives rise to one value of energy to the nucleus. So a nucleus can have how many energy values or how many energy levels? The answer is infinite. I mean, of course, it is finite, but if I have, let's say, n number of particles, there are many same, many different. So from permutation combination, they can have variety of energy state, isn't it? So given that how many energy state is possible for a given number of quarks, the configuration is really complex. I mean, it's very difficult to calculate that how many possible energy states are there. Maybe there are some advanced theory which can reveal it in a simple way, but as of now, I don't know how simple is this. So I will say it's very complex. Okay. So every configuration of UUD, or you can say DU, the up quark and down quark, a different configuration will give a different energy value to the nucleus. So a nucleus will have, I mean, technically you can say infinite energy state and hence infinite quantum state. And just like any other system, even the nucleus will also try to minimize the energy value to have the maximum stability. So generally the conversion of a neutron to into proton or proton into neutron is the result of stability. Okay. So they try to stabilize themselves and they do follow every rule which we have heard for the atoms, which means they do follow the Pauli exclusion principle. Okay. They do have the quantum states. They do have the variety of quantum states, which leads to the variety of energy values. So everything which you have heard about atom is equally true for the nucleus as well. Okay. And we have commonly heard about the nuclear disintegration, nucleus, you can say disintegration or radioactivity, which you call. Okay. So what is disintegration? Okay. Sometime in the process of regrouping of this UUD, DDU, they get detached from the main atom. Okay. So a part gets removed. If it is bulky in nature, then there is a Milken-Waldorf experiment which says that, okay, a bulky nuclei will not hold themselves together and so it will split. Now, if I want to split this DDU, UDD into, let's say, even two parts, in how many ways we can divide into two equal parts? This nucleus. Infinite. I can do like this, I can do like this, I can do like this. Now, every pair of half which I will create, can we guarantee that all half will have similar configuration? Which means, can we guarantee that the DDU of this part is same as DD of this part?
No.
Or DD of this part is same as DD of this part? Or
No.
DD of this part is same as DD of this part? We cannot guarantee. So what happens? Every nuclear decay will result into totally a disturbed state of nucleus. Kind of the DDU, UDD, the left out quarks are not in their best configuration. They are in the worst configuration. They are not in the lowest energy configuration. Okay. So these quarks will do transformation. So they will change themselves from up to down or down to up, depending on which one is the right way to stabilize the atom nucleus. So this configurational change, because generally nucleus will go from the high energy state to the low energy state, these are accompanied by some sort of nuclear reaction. Okay, so we have we call alpha decay, we call beta decay. So alpha decay is like disintegration, you break it down. Beta decay are quite interesting because alpha decay means you first break the nucleus, so you have now two collection from one single unit, you make two units. You can think a nucleus as a laddu, bundi ka laddu. You know bundi ka laddu? Have you heard? Maybe seen.
Yes, sir.
Yes, sir.
Let's say during Diwali I have a bundi ka laddu with two different color of bundi. So I take a yellow bundi and red bundi and mix it together, and then I distribute the laddu into two halves and I give it to you and give it to other. Okay. Can you guarantee that you will have similar configuration of red bundi and the yellow bundi?
No.
Okay. So one may be very happy, one may be very sad because you got a very less number of red bundi and only yellow bundi. Maybe you love for the red bundi. Quite possible. The idea is the red and the yellow is representing the up quark and down quark. So dividing a nucleus into two parts will not guarantee that we have similar number of the UD configuration. So you disturb the entire equilibrium configuration, which is demanded by the nucleus. A nucleus will demand you certain configuration to remain in stable condition. But if you disturb it, they will regroup together. They will undergo some transition. Okay. Alpha decay means you break the laddu and distribute to 2%. The beta decay is interesting. Beta decay is actually the conversion required to regain the stability or to go back to the lower energy configuration in nuclear dimension. So in nuclear world, we do have the quantum state, and these quantum states are again taken or is optimized. Okay. And if it is not in the optimal configuration, they go back to, they undergo certain transition These transitions are called beta decay. Every beta decay is actually meant for the transition of either U to P, U to D, the up to down quark and down to up quark. During this transition, okay, the nucleus as a whole may lose some energy. Okay, so when you go from a bad configuration to a good configuration, I'll tell you what is bad, what is good, as per some rules of physics. So when they go from the high energy configuration to a low energy configuration, they emit energy as a photon. This energy we call gamma radiation. Understood? What is alpha, beta, and gamma?
Yes.
Alpha is a name. Alpha is not a radiation actually. Alpha is a particle. So a particle cannot be radiation, but the stream of particle we call alpha ray. Alpha ray has nothing to do with the photon. Alpha ray has nothing to do with any radiation. Is this clear? Is this clear?
Yes, sir.
Yes, sir.
Now beta is some different. What is beta? Beta is the transitional play, the interplay of transition of up quark and down quark. That's called beta decay. Okay. So in beta decay, what will happen? You can expect up quark is transiting into down quark or vice versa. Okay. And what is gamma decay? What is gamma decay?
Energy release when it's going from a higher energy state to lower energy state.
Yeah. So it is like you rearrange your configuration of quantum state. So in a way, every nucleus is allowed to make or build their own quantum state. Okay. So it's like a restructuring of the quantum state in order to fulfill certain laws of physics. Okay. So that result, the transition from the high energy state to the low energy state, that transition results in energy release in terms of photon, and that we call gamma radiation. So I hope the meaning of alpha, beta, and gamma is clear. Tell me, alpha, beta, gamma is clear. What is alpha? What is beta? What is gamma?
Yes, sir.
Any doubt in this?
Sir.
Yeah.
Then what do you call the quantum of charge? Is it a quark or is it just an electron still?
See, again, it's like a matter of fact that, okay, whether you want to go back to the new quanta, which is 1/3, but again, if you assume 1/3 or 2/3, then everything can be re-expressed in terms of 2/3 and 1/3. So there is no problem actually. It's like either you stay with the electron for the purpose at hand, or you can go back to the quark modulus. But still, it will stabilize somewhere, isn't it? Whether you start from the quark level also, you have some number to multiply only.
Yeah.
Okay. So it is not a big deal. You will just multiply with a new number, and quantum state will become like 3/2 of the value of initial value, right? Let's say if you think that down quark charge has some value, you can express your answer in terms of down quark. But there is like a recursive model. So even the quark will undergo certain other model in which we have some other charges. Okay, so we have to stop somewhere and make it feasible to express to the world. So of course, in JEE level, we are going to take electron as the fundamental charge, and we will not bother about the quark model. But quark model is why I'm teaching, because it will make you understand a real life of nucleus. You can really understand what is happening, why these resistance are happening, and how the stability is guaranteed with such changes. Okay, so we'll see that. Okay. Now, what is important here is that this energy, this is very, very crucial. These two. So you can see the rest mass energy of proton is less than rest mass energy of neutron, isn't it? Because of the different quark combination. Understood? Yes or not? Do you realize what I'm saying?
Yes.
Okay. So just like we have heard about the spin quantum, spin angular momentum for electron, we do have the spin angular momentum for every quark. Okay. So we do have that. We do have the spin quantum number for nucleus as well. Okay. So we sometimes call nuclear spin. And these nuclear spins are very powerful method in the NRI, the nuclear resonance imaging. NRI is a technique again. So we do have something called nuclear spin. And what we can remember that just like electron. So I'll talk about something more about the relationship in atom and the nucleus. So just like electron move in an atom in fixed energy orbits. This is basically means the fixed energy orbits means fixed energy state. That is fixed energy state. These are models actually. Nucleons also. Nucleons. So we don't distinguish proton and neutron because that's called nucleons. Also occupy fixed quantum states. Okay. And they do possesses orbital and spin angular momentum. Okay, so the angular momentum is not only for electron. Angular momentum is also for
Nucleons.
nucleons. Okay. Not only that, they do obey Pauli's exclusion principle. Now, this is important actually. So, what is Pauli's exclusion principle? So, the two electrons cannot have all the four quantum states same, right? Isn't it? That's Pauli exclusion.
Yes.
So, to live together, one must have a different quantum state. Because if it is not so, then it becomes indistinguishable.
Yeah.
Okay, so it is like there is only one address and there are two persons living there. And we have no idea because we believe that one address belongs to only one person. So there is some kind of encroachment. And this encroachment is not known to the world. So that's like a miracle. I mean, I expect only one person and there are two persons living. So the Pauli exclusion principle is logical thing that every electron will occupy only one point of space, and saying that one space will have two electrons is impossible, right? It's like at one coordinate of space we have two persons living at the same time. Is it possible? They must have different coordinate, isn't it? Logically also you can think about. Okay, so let's say it is like in one coffin there are, okay, understood, there are two persons. And coffin dimension is same as for one person. So is it possible? The thing is, no, it's not possible. Assuming you cannot, compress and okay, do something. Okay, so they do obey the Pauli's exclusion principle, which means either two protons or two electrons, two neutrons, that is either two protons or two neutrons cannot have what? Or cannot
Same
have, you
quantum.
can say, or cannot occupy the same quantum state. Cannot occupy is better. Cannot occupy the same quantum state. But there's an interesting thing. See, it is forbidden for 2 proton and 2 neutron to live together. Okay. But 1 proton and 1 neutron can have or can occupy same quantum state. And how to explain this? But the nature is favoring the pairing. So 2 neutrons cannot have the same quantum state. 2 protons cannot have the same quantum state, but 1 proton and 1 neutron can occupy the same quantum state, which means nature favors pairing. So nature always, gives more stability to that configuration in which 1 proton comes along with 1 neutron. And now that there comes the issue with the Haber nuclei. In Haber nuclei, the neutron starts getting more and more in number. So it is like all protons are paired and still left with many neutrons which are unpaired. And that will bring high instability. Understood? So those excess neutron which we have there, I mean, they will start, decreasing the stability because they are now forced to live in the same quantum state and nature is not favoring it. So they will do some repulsion. I'll come to that. What is repulsion here? So can occupy same quantum state, that is nature favors pair. So nature favors pairing. It is clear? So pairing of what? Nature favors pairing of 1 proton with 1 neutron. Okay. Nature favors pairing with 1 proton and 1 neutron. Understood? The next point is the nuclear force is very short range force. I mean, that is again kind of a restriction. Nuclear force is very short range force and independent of what? Charge. So nuclear force do not obey the Coulombic repulsion, which means if you are within the world of nucleus, the Coulomb's law is not allowed to act there. So you may think that 2 protons will repel and so on, but the fact is the world within the nucleus is so strange that the mysterious nuclear force overcomes the Coulombic repulsion easily. But the problem is it is short range. So what is the like a drawback of this short range? Being a short range, what happens?
It falls off very quickly.
Yeah, so it means as the size of nucleus will grow, the peripheral nucleons will follow the Coulombic repulsion because they are beyond the range of nuclear attraction. So the problem is as we grow in value, like size, when we start crossing the boundary of the nuclear attraction, the Coulombic force will come into picture. And because the repulsion is tremendous, there is a high chance of breaking or disintegration. And that is the reason that a big nucleus decay easily under the Coulombic repulsion. Again, see, these are one of the regions, not all region. So it means some region will favor, some will be against. So we have to combine all the possible regions. So I'll talk about few regions that will, hold the stability. So some will support, some will oppose. So nuclear force is a very short range force. So that's why in a bigger nucleus, although I said that Coulombic force will not work, but when you cross the range of nuclear dimension, the nuclear force, the Coulombic repulsion will come into picture eventually. And that will bring instability. I'm not saying it will break completely. It will bring instability. But we need to look for other factors also. So there are many factors which will work together, and there is some random event in which one will win, one will lose. Okay. So there are some pro, there's some cons. So there are some support, there are some opposition for the nuclear to hold together. And when some factor dominates, it breaks. So nuclear force is short range force and it is independent of charge. So no matter how much charge is there, nuclear force will hold all such nucleons together. Understood? And it is much bigger than the Coulombic repulsion. So we can say the nuclear force is a mysterious force which is much powerful than Coulombic repulsion. So you can just mention this also as a point. So nuclear force is a mysterious force and much more 50 to 60 times powerful than Coulombic repulsion. Okay, so now again, this is giving you the reason that why alpha decay happens. The bigger size will induce the Coulombic repulsion into picture. The small size will cannot have the Coulombic repulsion. Okay. What else? Now we talk about something spin. So two nucleons can have same spin. Okay, now this is the contradiction part. When two nucleons will have similar spin, they have a strong interaction. Now it's a strange word. It's strong interaction. But if they have opposite spin, it is weak interaction. Now, do you realize the contradiction here?
Yeah.
It is the contradiction with the Pauli's exclusion principle. Pauli is not allowing for the state to be same. But the same state, let's say same quantum state, same spin angular momentum, will allow more interaction, the strong attraction. But it is against the Pauli. And where they are as per the Pauli exclusion, the interaction becomes weaker. Okay. So that's very interesting that two nucleons with same spin angular momentum will be strongly attracted, whereas two nucleons with opposite spin angular momentum will be weakly attracted. Now, this is the thing is they're not repelling, they are attracting, but the attraction level is weak and strong. So there is no repulsion. They only attract weakly and strongly. So that's again very contrast, relationship in the world of nuclear. That in one hand, Pauli is saying that no, you can't be having same spin. Okay, but that is also resulting that okay, because if you have same spin, it will decrease the stability. But the nuclear, the physics is saying that no, the similar spin will give more interaction. Very, very mysterious. Like why this is happening, still we are yet to figure it out. But this is like a fact, okay, which the scientist has come across through other experiments. So what we can say that two nucleons with same spin angular momentum will be is strongly attracted and opposite spin angular momentum will be weakly attracted. Now there is no repulsion. Only the attraction is strong and weak. Okay. Understood what I'm saying? So see, the nature is favored in the pair. I mean, nature favors pairing because the two proton coming together or the two neutron coming together will not be a good configuration. Okay. Because if they have same quantum state. So you can see that if you have a large number of neutrons and less number of protons, which is that the trend. If you look at the atomic number beyond 40, you can see that the jump of number of neutrons is much more than jump of the proton number, right? So atomic mass number will be almost more than twice, if you have seen. So
Yes.
for the less atomic number, it is double, but it becomes 2.5 times or more than that also, isn't it? So the atomic mass number becomes double, not double, 2.5 times. It is like the number of neutrons grows 1.5 times the number of protons. But in lighter, it is 1:1 relation. But in heavier, it is 1:1.5. So the number of neutrons. So what we have found, look at this. So for lighter elements, the neutron to the proton ratio, N/P ratio, is roughly 1. That's a very common trend. Like sodium 1123, calcium 2040, that's very much 1. Okay. But let's go to uranium 92 to 235. Is it double or more than double?
More than.
It's much more than double. It's like 2.5. So here we have the proton is 92. What is N here? Correct? So how much is this? 15 minus 2 or 5 minus 2, 3, 13. Then 13 minus 9,
43.
43. This is how much? 143.
140.
Minus 3. So 3. So 143. You can see the proton and neutron. So what is the ratio N/P? So for heavier element, the N/P ratio is roughly 1.5. You can check roughly. Can you check? (143 divided by 92). 1.55. Okay. So the problem is the moment you exceed the limit, the moment you exceed 1.5 also, what will happen? How to balance it out? See, for heavy element, for stability, I need a ratio of 1.5. So what kind of nuclear transition you want? Who should convert into what? If it is more than 1.5, let's say if N/P ratio exceed 1.5, what you want? To bring back to the value of 1.5? Isn't it? And to bring back the value to 1.5, what you want to change? What kind of change you want? The neutron has been really more than proton by a value which is much more than the stability condition. This is the stability condition. Like it is roughly this. So if N/P ratio is much more than this, which transition you will favor? Conversion of P into N or N into P? Which conversion you want here? Tell me.
N to P.
Which conversion will favor? You want to decrease the ratio, no? So you
Yes,
will
yes.
you want for some of the neutron to convert into proton.
Yeah.
So when a neutron will convert into proton, we are going from high energy, high mass to low mass, as per the quark model, if you remember.
Yes, sir.
So when you convert from neutron to proton, you create some charge. And for the charge balance, I need to create a particle with a, because this is 0, 1, this is 1, 1. What I need here? Which kind of particle for charge balance? 0 minus 1. So what is 0 minus 1 called?
Electron.
Electron. Understood. So this is called beta minus decay. And the beta minus decay will be accompanied by some energy release, isn't it? Because if you add the mass of proton and electron, it is still less than the mass of neutron. So some energy will be released. And this energy will be released in terms of photon. This photon is called anti-neutrino. We'll come to this again, don't worry. So this is called beta minus decay. And the beta minus decay generally happens to balance the N/P ratio close to the stability region. And beta minus decay occurs when the number of neutrons is really high, which means alpha decay has occurred. Okay, so you got the laddu party, if you remember the laddu, the yellow bundi and the red bundi. And let's say the yellow is representing the neutron and the red is representing the protons. In your part, which you received after the breaking, when I distributed, you got mostly yellow one. So you have excess of neutron and less number of proton. So there are many things which are getting violated. First, the Pauli's exclusion principle, because we have less number of pair. So less pairing means definitely less stability. Okay. And the Pauli will try to avoid the quantum state same. If they avoid the quantum state same, then it means the remaining left out neutron will try to make the spin opposite, isn't it? Are you getting this point, what I'm saying? Because only by making the spin opposite, you can stay together. As per the Pauli exclusion. But the rule says that opposite spin will have weaker interaction. Yes or no?
Yes.
So it means they can stay together, but with very weak attractive power. It means their stability is less. So if you convert some of the neutron into proton, you can do two things. First, you will increase the pairing. Now they can live with the same spin and they can strongly attract each other, which in turn the nuclear will become more stable. The whole purpose of decay, it is to go towards a bigger stability, to attain a greater stability. Understood? The N/P ratio sometimes goes below 1, which is again dangerous. In such case, we need to decrease the proton, increase the neutron. So some of the proton must convert into neutron. So what we need here? A +1. So this is called positron emission. Now these reactions do not occur independently. These are the reactions which happens inside the nucleus, because if you look carefully, this reaction is against the conservation of energy, isn't it? Do you realize this? Realize this, what is happening here? You're converting a low mass into higher mass, isn't it?
Yes.
because it is a proton which is less in mass, neutron is more mass, and then one extra electron also. So we are going from less mass to high mass. So we are increasing the total rest mass. And therefore, nature will not favor such kind of reaction. And we'll come to that. The nature will have a better way of handling such situation. That's called the K electron capture. So we'll come to that.
This is without any external energy supplied.
No. This is within the environment where energy is available from other source.
Okay.
And this is called neutrino. It is like you need a car to run away from some war area. Okay. You don't have money to buy a car, but you can find some abandoned car. What will do? We'll take that car and we'll run away. Okay.
Yeah.
So within the nuclear, because there are so many reactions going on, there's a lot of energy getting released. So nature will have some randomness in which you may captures other energy and bring out this reaction. But the probability of such reaction is rare. That's why the positron emission is a rare process. But it is a process which exists in nature. And this is also proof the fact that we can convert energy into mass. That is precisely the Higgs boson. Okay. So in the Large Hadron Collider in 2012, when we had the God particle, okay, so that reaction was actually meant for the same. In that reaction, we were trying to prove that the energy can be converted into a mass. Because Einstein said the other way around, the mass can be converted into energy and you can make the nuclear bomb. So for every action, the nature will have the inverse process also. So that is the whole idea about the God particle. Okay, so we'll come to this, the positron emission, which is a very rare condition in nuclear physics. But there is a better one, which is more famous, called the K electron capture. We'll come to that. Okay. So excess proton means what? The nuclear will have very strong charge. It means the orbiting electron in the K shell are highly insecure, isn't it? So let's say sometime the proton comes to the periphery of the nucleus, because within the nucleus also the proton can go anywhere, right? So imagine due to some randomness, the charge density appears near the edge of the nuclear periphery, hypothetically you can assume, and suddenly the attraction between the orbiting electron and the nucleus grows in value because of some asymmetry, getting appearing due to some random process, which we don't know. This extra force developing will be able to pull the orbiting electron into the nucleus. It is like you will eat away the nearest orbiting electron. So that's why it's called the K shell, K electron capture. Also, a very, very powerful nuclei is very dangerous. It may, disrupt the configuration, and you can know that once you remove the K shell, it will undergo a series of reaction, a series of transition, isn't it?
Yes.
Because once you make the empty space vacant, then it can cause a series of transition. So see, nature is having a lot of issues. So it is balancing something by some logic. So we can only identify the logic by one way or the other way around. We do not have the exact idea that which logic is getting more powerful. So we can only say that every logic will have some contribution. So now we are going towards the contribution part. That how we decide the nuclear stability. That's today's question. All right. So a lot of issues within nuclear world. So before we delve in deeper into the world of nucleus, I would like to introduce you something basic idea of nuclear dimension. What is nuclear dimension?
10 raised to minus 15 meters.
So can we assume the nucleus to be a spherical body? So for any spherical body, the dimension will be expressed in terms of radius. Yes or no?
Yes.
And can we say the size of the nucleus will be proportional to the number of nucleons? Can we say? Because if you bring more number of nucleons together, it will have bigger size. That's logical, isn't it? So we say that volume of a nucleus is proportional to number of nucleons. Yes or no?
Yes, sir.
So you can say 4/3 pi r cube, which is r cube, is proportional to a. So r will be proportional to how much? The cube root of number of nucleons. So r is equals to, and the value of r naught is 1.1 fm. What is fm?
Femtometer.
Femtometer, fermimeter.
It is minus 15, right?
Yeah. So that is the smallest nuclear dimension which we can have. That is for the nucleus of hydrogen atom. And that is precisely the dimension of, or you can say, the radius of proton also, isn't it? So what is the radius of proton? Because the hydrogen nucleus is made of only one proton, isn't it?
Yes.
So radius of proton is r naught, which is, isn't it?
Yes, sir.
Okay. So we'll talk about density. These are small calculations. I mean, one should be aware of. So because nucleons are close together, no matter which element you choose, inside the nucleus of that element, you will get only number of nucleons. But what will happen to density? Will it be same or different for every element? The density of nucleus of every element is same or different?
Should be maintained.
Yeah, it is going to be maintained because it is made of nucleons, which will maintain the density. So density of nucleus is constant. Okay. So what is the density of nucleus? Mass per volume. Okay. So what is mass? So because density is going to be same, you can choose any element, you can add any volume. So we can add mass equals to mass of neutron into atomic mass number, assuming roughly neutron mass is same as proton mass. Can we write like this?
Yes.
And volume 4/3 pi r cube. And the r cube itself is how much? R naught cube into a. So no matter which element you choose, the density is same, comes out to be constant. Mass of neutron, we know it's 1.67 10 power minus 27 kilogram, right? 4 by 3 pi is roughly 4. Just make it simple. 1.1 whole cube minus 45. Am I correct? Femtometer. No? How much is this? 45 minus 27. Tell me, guys. So this is roughly how much? Can you tell me the rough answer? I know the answer, but you can tell me by doing calculation. Tell me, guys, how much? Okay, you can do the calculation, but remember this is roughly 3 into 10 power 17 kilogram per meter cube.
Yes.
So this value you should remember. This is very important. The order is 10 power 17 kilograms. What is the mass of Earth? Mass or density of Earth? Okay, I'll tell you from the Wikipedia. Density of Earth. Oh my God, very bad. It is roughly so how denser is nucleus with respect to Earth?
Ten raised to 14.
So roughly I can say 10 raised to power 14.
Yeah.
My God. So to create equivalent mass of Earth, how big nucleus we need to have? Let's equate the Earth mass with the nucleus mass. So mass of Earth is 5.96 into 10 power 24 kilogram. Roughly you can say 6 into this. So I can say this is 6 into. So density of nucleus into volume, which is 4 by 3 pi r cube, is roughly 10 power 24. So this is 3 into 10 power 17 into 4 by 3 by r cube. Okay, so who will tell me this answer roughly? So r cube is how much? 6 by 4 pi 24 minus 17, 7. So roughly it is 60 by 4 pi 10 power 6. So r equals to the cube root of 60 by 4 pi into 10 power 2 meter. And 60 by, okay, just let me tell you the value. 60 by 4 pi 1.68. So to balance the Earth mass by as denser as the density of nucleus, we need a sphere of what radius? Roughly 168 kilometers, 168 meters only. So if this is Earth, what is the radius? 6,400 kilometers, isn't it? And how much we need to balance by the nucleus itself? How big nucleus we need? 168 meter radius, right? So 6,400 kilometer and 168 meter, you can imagine. So maybe 1 teaspoon of nucleus 1 teaspoon of nucleus is as good as Earth. Do you realize this? Maybe you can realize. 6400 upon 168. How much is the ratio? The radius of Earth and radius of nucleus. This is tremendous. Roughly 38,000. So this nucleus is nothing but your neutron star. So what is neutron star? Anyone knows what is neutron star?
Yes, sir, I guess.
Yeah. So what happens due to the very strong gravitational attraction, the Earth size, the size of the star will keep on shrinking, and at a time will come when the gravitational force will become so powerful that all of the orbiting electron will be captured by the nucleus of corresponding atom, and therefore the existence of atom will go away. What you are left with is
Forms
only
a black
neutron.
hole or something, huh?
Yeah, black hole will form after this actually.
Okay.
So from the red giant to white dwarf to the neutron star, and then we'll go to the black hole. In case if you exceed the Chandrasekhar limit, if not, it will break into supernova. So what is Chandrasekhar limit? If the mass of the star is more than 1.4 times mass of sun, black hole will form. Else, supernova. Understood? So the nucleus is nothing but the density of neutron star. You must remember that a neutron star is nothing but a collection of nucleus. So in case of neutron star, the atom, the concept of atom will not be there. What you are left with is just nucleus. So imagine if neutron star is so dense. You can imagine what is the density of black hole. Okay, so it's really dense. Anyway, so this idea should be borne in mind because you may get some informative question about nucleus and its various purpose. I hope the size is clear. How we represent nucleus? How to represent the mass of nucleus? So we do not know the mass of nucleus. What we know is the mass of atom, because we don't have the isolated nucleus existing in the world. So what we have is atom. Okay. So for every atom, you can choose a symbol X. You write the atomic mass number here and atomic number here. So what do you call this? Mass number, atomic mass number, mass number. And what do you write here? Atomic number. So mass number is basically the number of nucleons. Count of nucleons. Is this clear? So what is A? Atomic mass number, which is the count of nucleons. What is Z? Only atomic number, which is count of what?
Protons.
And luckily we know the mass of so this is called mass of X atomic element. So what is the mass of nucleus? So what we must subtract in atom to get the nucleus? Tell me. What we must subtract
Mass of electrons.
and how many
Z
electrons? Yeah, so we have Z times M. So this is how you write the mass of nucleus, because there is no way to write the mass of nucleus. Or you can write the other way of writing is Z time mass of P. Z time mass of P plus A minus Z times mass of N. But the thing is, are they equal? Are they equal?
No.
No. So the question is why they are not equal? Why they are not equal?
Because of some extra energy, binding energy.
Yeah, because the creation of any entity in the universe is a result of attaining the better, or you can say lower energy configuration. So the rest mass will change, and that is the loss of rest mass in the transformation process from the nucleon to the nucleus or vice versa. So when you create something from nucleons, so if nucleons coming together forming nucleus, this event cannot be the real event, cannot be the, you can say, uh, spontaneous event, unless it is going towards the better energy configuration, or you can say lower energy configuration. So the nucleon's mass we cannot equate with the mass of nucleus. There is always a difference. However small the difference may be, but that is sufficient for the creation to happen. And the difference converts into energy, which we call binding energy. So the next concept here is binding energy. Anyone who finding that I'm in a situation of getting asleep now, because I want to extend this lecture. If you all are okay. If you have any objection, then we can continue this lecture. So convection.
Yes, sir. Sir,
Yes,
will
sir.
we be finishing the chapter today itself?
Pardon?
Will we complete the chapter today itself?
No, impossible.
Okay.
It will take some time.
Okay.
So I'm trying to cover some basic part, then just one concept. So what is binding energy? So nucleons coming together. So independent nucleons come and form a nucleus. In this case, it will release energy. So minus means it will release. So they lose some energy and form nucleus. Or to the nucleus, which is already in place, add energy and make them independent. So there are two ways in which you can find the binding energy. So what are the two ways in which you can define binding energy? It is the amount of energy released during the formation of nucleus from its constituent nucleons. Or what? Who can define the other give the other definition? Anyone?
The amount of energy required to separate the nucleus into its constituent nucleus.
Yeah. So it is the amount of energy required to break the nucleus into its constituent nucleons. Okay. So both are the definition. In one case, it will release. In one case, you have to impart. So if you have a well stable nucleus, if you want to break it, you need to provide the energy. Or if you have nucleons, you have to extract that energy away, or it will form the nucleus. Okay. So binding energy is also a quantity which contributes towards stability. Okay, so we will talk about stability in a while. So let me define this binding energy quickly. So first definition, it is the amount of energy released in the formation, in the process of formation of nucleus from its constituent nucleons, right? Or what you can say, it is the amount of energy that must be supplied to the stable nucleus to break down into its constituent nucleons. There are two ways of saying. Oh. Okay, so the definition is clear. Now, any process in which more energy will be released, we may think that, okay, it will be more sure. But is it true? So can we guarantee that more energy released in the process of formation of nucleus will also guarantee higher stability?
Maybe.
Maybe, but not sure, right?
Not sure.
The reason is the stability depends on a factor called binding energy per nucleon. So stability is not just the function of binding energy, but it is called binding energy per nucleon. So we need to check not just binding energy, but we need to check that how much binding energy is released per nucleon. Understood? It is like we have two chapatis, and if you have one cube of butter, and someone is having 4 chapati and the same cube of butter. So which butter or which chapati will be having more butter?
Two
One
chapati.
cube, 2 chapati, 1 cube, 4 chapati.
Two chapati.
So the idea is that the binding energy is like the butter, and the A is like the how many chapati you are having. So per nucleon will tell you the better stability. Okay, not just binding energy. Because if you bring a large number of nucleons, the binding energy will keep on growing. In that way, the heavier the nuclei, more the stability. But is it true? Because bigger the nucleus, more the binding energy, isn't it? Isn't
Yes.
it? So in that way, stability should keep on growing. But it is not found, right? So what we found is what against? We found that it will grow with, of course, number of nucleus. But only after some time, it will, after some limit, it will start decreasing also. So the binding energy. So when you plot the graph of binding energy per nucleon, okay, with atomic number, the graph is interesting. It will go like this from 1, 2, 3. We'll have peaks, then we decrease and then reduction. This is a typical graph of, and which is having the highest binding energy per nucleon. Do you know this element?
In
Iron.
Iron. 26. So the nucleus of iron is most stable. Okay. So binding energy per nucleon gives the stability graph. And you can see as Z will increase, so you can say stability is not continuously increasing with Z, rather it is decreasing also. So what really matters is the binding energy per nucleon. So you will be asked in the examination that which of the following will have more stability. So you have to find out the binding. They will give you binding energy, of course, because it's a simple question. So they'll give you binding energy B1, B2, B3, A1, A2, A3. Just take the ratio, compare it. The bigger the value, more the stability. Simple, fair enough. Perfect. So now we'll talk in more detail, like on what factor binding energy depends. Like we know that this will grow with time. I mean, grow with Z first, then decrease also. But now we are going to exclusively talk about factors affecting binding energy. Okay. So we'll talk about binding energy versus stability. So there are three effects that we talk about. The first is called volume effect, which simply means that binding energy will be proportional to number of nucleons coming together. That's logical, isn't it? So as A will grow, B will grow. Yes or no?
yes,
And therefore, the B, let's call B1, the first factor, because this is the first factor. So B1, okay, upon A will be some constant, because this is proportional. We can say this is some constant. Okay. So let's call this constant A1. So volume effect will be like the stability will be constant due to this particular effect. Okay. But if this is the only effect, then things will change. Then all will be equally stable. Like if the B1, B by A is same for all, then things will be very complex. I mean, then it's difficult to compare which one is more stable or less stable. So comes the next effect called the surface effect. You know what is surface effect? Can you guess? The nucleons near the surface of the nucleus are less under the influence of nucleus and more under the danger zone of, you can say, nuclear range. So they are about to break the range in which the nuclear force operate. Okay. So as surface area will increase, what do you think? As surface area will increase, it means a large number of nucleons will be on that surface, can occupy that space.
ha,
And those are not surrounded by other nucleons. So they are like bringing about a lesser stability. They are like kind of breaking element. They will break the stability. Like more the nucleons on the outer periphery, it's very dangerous. And the reason is simple. They are dangerous because the repulsion will break it down. So Coulombic repulsion will act on those elements, I mean, on those nucleons. Okay. And because of those Coulombic repulsion, they can easily disintegrate. They can easily go beyond the nuclear dimension. So can we say that the surface effect will kind of decrease the stability? Can we say? Yes or no? Do you realize what I'm saying?
Yes.
So the Coulombic repulsion will come into picture. Okay. So what happens as we have more number of, as the surface area will increase, the Coulombic repulsion will act and it will eventually bring instability to the nucleus. Understood? So it is not a good thing. Do we want this to be more? The answer is no.
No.
Okay. So we can say that more the number, more the surface area, more nucleons will occupy that surface, and these electrons may cross the nuclear range, hence bring instability. Because they will break it out, they will just break out. So we can say the second factor will decrease, but this will be proportional to what? Surface area, and surface area will be proportional to R square, isn't it?
Yes.
And we know R square is, the formula was R is equals to R not A power 1/3. So R square becomes proportional to 2/3.
2 by 3. Yeah.
Since R is R not A. So we can write, it's in space. Look at this. So minus BE2 is proportional to A power 2/3. But since we are talking about stability, so we are talking about BE2 by A. Let's bring some constant. So this will become A power minus 1/3. Can we write like this? 2/3 by A. So 2/3 minus 1 is minus 1/3. Or you can say A2 by A/3. Is this clear?
Yes.
And the third is called Coulombic potential energy. So as we grow as the number of protons will grow, it is dangerous, because proton will have charge, and this charge will have potential energy. And if you remember the mutual potential energy formula, do you remember the mutual potential energy formula for two charge particles? K Q1 Q2 by R square.
Yes, sir.
I hope you remember the potential energy.
Yes.
So in case of nucleus with atomic number Z, how many protons we have?
तो potential energy के लिए R आएगा, not R square.
हाँ वही.
R. So in case of nucleus, if the atomic number is Z, how many interactions will be possible?
ZC2.
ZC2. So number of interactions we can say Z into Z minus 1 by 2.
Yeah.
And every interaction will have the interaction of E square.
Yes.
And then we can add the R average. What is the average separation between the two proton? So the nearest proton will be 0 separation roughly. And the farthest will be 2R. Isn't it? So then the separation will go from where to where? 0 to 2R. What is the average? Come on, the average is R only, na?
R.
So the average separation we can add average separation we take as 0 plus 2R by 2, which is R. And this interaction will grow in potential because these are positive charge, so potential will grow. So the binding energy means we have to decrease the energy, but more the charge interaction, it will grow the value. Therefore, the third Coulombic effect will also decrease the potential, and it is going to be proportional to Z minus 1 by 2 E square by R. And we know that R is A power 1 by 3, isn't it? So minus BE3 by A will be how much? Some constant into Z into Z minus 1 by 2. I'll keep it this way. E square by A power 2 by 3. No, 4 by 3. Am I correct?
Yes.
Therefore, so we can take E square also in the, because E square is fundamental constant, so I can take this as constant itself. Let's keep only the factor which can affect. A3 will contain everything. And I would like to show you Z actually, okay, in the expression. So can we say that, because Z will also matter. So now we can say these are 3 factors. There are many more factors, remember, but up to our JEE preparation, I'll keep up to 3 because that is the level of Verma-ji. So Verma-ji has taken up to 3 level, and in other books also, Verma-ji has taken from the Arthur Beiser, which is also taken the 3 level only. Some other books has taken 5 factors. So binding energy per nucleon is a combination of A1 minus A2 A power minus 1 by 3 minus A3 Z minus 1 by 2 A power minus 4 by 3. Do you realize this? So binding energy, or you can say stability, is not only depending on one factor, it is depending on multiple factors. That's why this relationship is kind of complex, not very easy. So stability, if this is a given graph, okay, so they may ask you that for what value of A, you will have the best stability. Okay. So kind of you can differentiate and you can get the relation, and they may give you some other relation of Z and A also, that assume that Z is equals to this A, find the stability. So it could be a differentiation question where you need to differentiate with respect to A and to get the value of A which can give you the best stability. And I think kind of this mathematical framework is justifying the graph also. That's why this is accepted one. Okay. So up to this point, I think any doubt in there? Any doubt in theory?
No, sir.
Okay. So remember up to this point, and rest we'll study in the next lecture. Because anyway, this will not end today. It will take complete one lecture to finish the reductive. Theory is this much only. This is the actually very strong theory, because you need to know this theory. Otherwise, you won't be able to answer the conceptual question in nuclear physics. Solving numerical is one thing, but to answer the conceptual question, you need to know this small detail, what goes inside the nucleus, why decay happens, why alpha decay, why beta decay, why gamma decay, Okay, so you can find yourself in a comfortable position. So before we end, can we start solving the conceptual programming question from objective one? At least we can solve some question up to 10. So objective 1 to 10. 10 minutes sufficient?
Yes.
Okay. So that is the red activity after that. So that I haven't taught you. I think 10 minutes are done. Okay. So let me tell you the answer for 1 to 10. 1A, 2C, 3C, 4D, 5A, 6B, 7D, 8B, 9D, 10D. So all 10 correct. So we start with the all 10 correct. All 10 correct? Anyone? Okay. More than 8 correct? 8 or more than 8? 8 or more than 8? No one. 7 and more than 7? Okay. Above 5, 5 to 7. 5 to 7. 1 to 5. 1 to 5, correct. Only 1 to 5. Less than 5. Less than 5. Yeah, so you can ask a doubt. Tell me.
1, 6, 7.
6 will be all equal. That's simple because within the nucleus there is no distinction of neutron, proton, neutron, whatever. So all
But you
force must be
for
equal.
the pairing, right? Like one proton and one neutron are more favorably paired. So
No, that is different thing. I mean, inside the nuclear force, you're not supposed to distinguish the force. So how they are interacting is a mysterious in nature. No one knows how exactly they're interacting. So we believe that all are interacting in a same fashion. Nucleus do not, kind of is biased towards the kind of force it applies. Okay. So question is, these denote the magnitudes of nuclear force by a proton on a proton. So these are nuclear force, not the Coulombic force. Okay. So all must be equal.
okay.
In the question number 1, it must be less than 12 U. Why? Because in the formation of an atom or nucleus, some mass will be lost.
So the answer is A.
The mass of neutral carbon atom in ground state is. They're asking the atom.
Yeah, understood why it's A. Why it should be A. I guess.
Yeah.
Because one unit is defined per carbon atom. So
Yeah, it is defined for atom itself.
so it should be exactly A. Got it.
Yeah, it is not for the nucleus. The 1/6 and then other
7.
7. Let FPP, APN, this denotes the magnitudes of net force by the proton on proton. Now the net force means the nuclear
Coulomb.
force and other force. Yeah. So what will happen? Which option?
Proton will have Coulombic force as well.
Yeah.
So what was the pairing that you talked about between proton and neutron? Or is that
No, the nuclear, the arrangement of, you can say, proton and neutron within the nucleus. So nature favors pairing means it wants that we should have equal number of neutrons and protons within the nucleus.
okay?
But as you go to the heavier elements, what happens? The proton will be lesser, much lesser, and the neutron will exceed.
Yes.
So now the pairing is not possible for everyone, right?
Yeah. Okay.
Lecture is over. Yeah, you can leave. Lecture is over.